Hi there. Today we are going to talk about a simple microfluidic phenomenon called diffusion. Diffusion is a mass transport phenomenon that occurs when there is a concentration gradient. In diffusion, the regions of higher concentration will travel to regions of lower concentration until there is no longer a concentration gradient. Diffusion can be conceptually understood as the natural consequence of Brownian motion. The molecules within the system are constantly moving, propelled by thermal energy. As a result, the molecules will spread out until they are eventually evenly dispersed. We decided to confirm that thermal energy, or heat, is related to the rate of diffusion. To test the effect of temperature on fluid diffusion, diffusion flux is measured at different temperatures. In Fick's first law, diffusion flux is directly proportional to the diffusion coefficient, since molar concentration does not change significantly over a small radial distance, and thus can be assumed to be a constant. Diffusion time interval is set to be 30 seconds in each experiment, which is measured by using a stopwatch. A greater radial diffusion distance indicates a larger amount of fluid is diffused through a cross-sectional area at a given amount of time, thus a greater diffusion flux. The experiment is performed with the same dye concentration, but at 3 different temperatures. In this case, the concentration gradient is assumed to be identical for 3 experimental setups. Therefore, the diffusion flux of the fluid is solely dependent on the diffusion coefficient, which is essentially a temperature-dependent term, as suggested by the Einstein relation in kinetic theory. The 3 temperatures of interest are chosen to be 0 degrees Celsius, temperature of ice-water mixture, 25 degrees Celsius, room temperature, and 100 degrees Celsius, temperature of boiling water. These 3 temperatures can be obtained readily without using a measurement device, such as a thermometer. A green food coloring dye is used as the source of the diffusing fluid in water. The same dye dropper is used throughout the experiment to ensure the consistency of the volume and concentration of the dye. A small amount of water is sprayed on one side of a cutting knife. In the first setup, where the diffusion flux is measured at 100 degrees Celsius, the knife is preheated to 100 degrees Celsius in a pot of boiling water for 5 minutes. To minimize heat transfer, a thick piece of paper towel is put in between the knife and the surface of kitchen countertop. For the experiment to be performed at 0 degrees Celsius, the knife is submerged in an ice-water mixture for 5 minutes for it to reach the desired temperature. A piece of thick paper towel is again used to minimize heat transfer. No specific anti-heat transfer setup is required for the experiment performed at room temperature.
Although there is some preparation involved, running the experiment is quite simple. First, we coat the surface with a layer of water so that the dye will have a solvent to diffuse through. Second, we add a drop of dye and start our 30-second countdown. At the end of our countdown, we carefully measure the diameter of the dye with a ruler. We record our results and plot our results on a graph to determine a relationship. Our calculated results show that the rate of diffusion is clearly larger in the 100 degrees Celsius experiments, and that there's a slight difference between the 25 degrees Celsius and the 0 degrees Celsius experiments. Visually, the 100 degrees Celsius diffusion appears to be much larger than the 25 degrees Celsius and the 0 degrees Celsius experiments as well. When the averages of the 3 results are plotted, there's a rough linear relationship between the 3 results, which is in agreement with the equation that Einstein revealed in 1905. This concludes our presentation. Thank you for listening.